Wanted to talk to you about architectural engineering tonight. So very different skills best done together. And there's a bit of controversy around left brain, right brain theory, but I happen to believe it. That's, different parts of the brain anyway. And we do a bit of reading and research on it. We think very differently and we communicate very differently. So architects are very much more visual. You see the greater complexity are very divergent in their thinking. Engineers tend to be far more spreadsheet type thinkers, very good with data, see the world in numbers and trends, and are very much more convergent in my approach. So I think it's amazing to me that I graduated from university and found myself sitting around a table expected to work with architects, feeling like I was speaking a different language. And it used to be the same thing, and this is what came of it when it was the same thing. Fantastic results. This is St. Patrick's in New York. So these things were designed by stonemasons, and everything comes together to form something that really is truly architectural engineering. So it's designed to really inspire the populace to believe that there's higher forces around and that they should be actually submitting to the church and all of the rest of it. And I really like this image just because everything that we have today is actually in that picture. So in the middle you've got the stonemason, who is probably the designer, the contractor, even the supplier, working on all the building. Off to the left you've got the church, who's the client, and then you've got the knight, who's the king's representative, probably the equivalent of the BCA, maybe the step in if something goes wrong on the way through. But the point is, it used to happen because it was just, very few number of people, and it used to happen sort of naturally. But projects got more and more complicated, as they should, and we needed more and more people on board to actually look at the complexity. And so now we're in a design environment that is very fragmented. And I think we've lost a lot. We've obviously gained a lot, but there's a lot to be gained through what we've lost, if that makes sense. I'm going to speak about projects in Singapore just because I spent 8 years there, and that's really where I started to think about architecture and engineering. This is Singapore back in the 60s, I think, the coastline. This road you can see up on the top here is Beach Road. It's so called because it's by the beach. And when I arrived in just after 2002, that's what Singapore looked like. So they'd reclaimed about 3 kilometres of land out into the Singapore Straits. And strangely enough, Beach Road, where Arab's offices were just up here, there's still shops there 30 years later selling fishing nets and that sort of thing. So the land changes quite quickly, but the commerce lives on. Okay. So Singapore, for those of you who know, is really the centre of gravity is around the Singapore River in Clark B, up through the left here. But through 2004 onwards, they built a whole series of really ambitious projects which moved the whole centre of gravity of Singapore from the river to Marina Bay. That's what it looked like when I first arrived. It's the advantage of a benign dictatorship, a democracy with one party that actually can make decisions based on a 30-year timeline to actually reclaim land for the future of the country. And that's what the brochures said around Marina Bay Sands, and effectively what the Singapore government wanted to build. And it doesn't look too far different to that now if you go to Singapore. It's an incredible feat. Huge amount, billions and billions of dollars worth of construction happening very quickly. So the projects I was going to go through today were the Marina Bay Sands is the top one, casino from Sheldon Nelson in Las Vegas, the Singapore Flyer, the big observation wheel, and then the Singapore Sports Hub, which is just next door to Marina Bay in Culling Basin. Hopefully I'll include a bit of technical stuff in there, but I really wanted to talk a little bit about just the interplay of architecture and engineering and what the drivers were on the projects, and really for you to make up your own minds about how these projects happen, because you all will be involved in projects and be aware of the drivers and those at the same time. So Marina Bay Sands was a behemoth of a project. It was a 3-month competition, and there were 5 or 6 different casino consortiums around the world all bidding for it. It was awarded in 2006, finished about 4.5 years later, $7 billion US, 5.5 billion US, 7 billion Singapore, which for a building project is large. In terms of design motivations, pre-award, it was all about urban activation. So the Singapore government had made this big decision. It was probably Lee Kuan Yew that made the decision that gambling was probably okay now. And so the Singapore government actually opened up 2 casino licenses in Singapore, one for Marina Bay and one for Sentosa Island, which is sort of the resort island to the south of Singapore. But they were keen that it wasn't just a casino. It needed to contribute, like everything in Singapore, contribute to the betterment of the country. So it needed to feed the economy and actually make things work. Architecture was very important. All the casinos wanted to wow. There were some consortiums who took out television space advertising their bids before the announcement, just trying to swing. So I put dollars there in dark grey just because actually I think that they were figuring out how much they could actually spend and still get money back from it. So it's almost like spending as much as they possibly could to win this cherry project, because Singapore is a stable geography in Asia where people really like to gamble. So it was really seen as a cherry project. And to put it into context, the Sands Corporation, their casino in Macau, paid for itself lock, stock and barrel in 9 months. It totally paid for itself. And so that's, I think, actually to cut through, I think in Singapore it ended up taking them 3 years or something like that, but it's a huge money-making machine. Post-award, it very quickly just turned to time and fulfilling obligations. So again, money was not the main factor, but they needed to actually get the casino operating so they could actually fund and start paying back this debt. I think at the time, it was, they went through the global financial crisis and they hit some really tough financial times. So Las Vegas Sands share price went from something like $90 down to $6 at the time. I remember thinking maybe it'd be a good idea to buy it and never did, but some people on the project did. And I think it went back up to about $120 after that. So that's all right.
Sorry.
Just my controller again. Oh, here we go. So it all became about time, because time was money. And so it was not how cheaply can we build things, but how quickly can we get things in place, which a lot of the time is actually the same solution, because the quicker and simpler something is to actually build, the cheaper it is to build generally as well. But the other one there was fulfilling obligations, and I came away from Singapore with immense respect for the Singapore government. So the URA, or the Urban Redevelopment Authority, the planning authority in Singapore, and they ran the competition, and they had stenographers around the room in all of the presentations that the casinos were giving to the government as to why they should be winning the work. And even outside of the contract, to demonstrate that point, about 3/4 of the way through the project, right back at the start, Las Vegas Sands said, we'll build you the biggest ballroom in Asia. And someone in the URA found a bigger ballroom. And they actually forced them to tear down what they've done, redesign it, and actually build a bigger ballroom to fulfill that verbal promise made in one of those meetings. But the URA looks after the architectural project, and I saw them drag architects in as an engineer and actually read them the riot act and actually have a positive effect on planning, I thought, anyway. This is the project. So it's there's 3 huge buildings down in the podium base: the meetings, incentives, conventions and exhibition centre, the casino and the theatres. 1.4 kilometres of retail mall around the outside. 3 55-storey hotels with the Sky Park on top, which I'll talk a bit about, the Art Science Museum and these crystal pavilions out in the harbour, and a movable promenade which goes up and down for events. And just to make it even more complicated, an MRT line running through the middle of it. That gives you a scale of the Sky Park in terms of steelwork sitting on top of these towers. Basically 340 metres of steelwork perched on top of the towers with a 65 metre cantilever at one end. And all of that supporting a 150 metre long infinity of swimming pool. So Moshe Safdie was the architect, and that was his masterstroke, was to say a 5-star hotel should have grounds and parks and a palatial pool. And yeah, it's very difficult to get that in Singapore because of the value of land and everything's so compact, so you just lift the whole thing up on top of the tower. All of that built on 35 metres of reclaimed land and marine clay, which is the equivalent of, there's more geotechnical people in the room than me, I guess, but toothpaste, I understand, probably the equivalent of Cood Island silk in Melbourne, so under consolidated clays that just keep on settling the moment you put in the load on. So talking about the Sky Park, these are the towers. It's pretty traditional design, the orange lift pores, and then these big concrete shear walls in between every second room line. There's two sides to the walls, so they actually split at level 23 to provide this huge atrium that runs through the middle of the building, which is great normally, except that we all know that concrete moves and it's a living, breathing material. Because there's out of balance forces, there's quite large structural forces, even just from the dead load. So from a city that's used to building just straight up and down to actually start building sideways brings in a few issues. And the way that was dealt with, we actually put in these big linking trusses between the two shear walls to actually make it work as an A-frame. So that's then there. The big trusses rolled with 60 and 80 millimetre plates that were embedded into the shear walls. And of course, all of this is supporting an infinity edge pool up on top. So we did a lot of work was put into trying to estimate what the deflections were going to be both during construction and in operation, just to make sure that the pool would be okay. And there's some of the graphs you can see. Up until level 23, it really starts to take off there to the left. The moment you hit level 23 and put in those big trusses, it sort of stabilises it. And then as you add more weight, just the weighted geometries, it actually starts to self-correct and gets back up to something close to where you want it to be at the top. But even with all of that, just under dead loads, those towers moving up to 60 millimetres sideways in the permanent condition. And then you add on top of that, just under wind, they're moving backwards and forwards by 200, 250 millimetres, and officially there's no such thing as earthquakes in Singapore if it's covered by a 1% national load, but actually for towers this is important to look at them properly, and actually under earthquakes they're moving up to half a metre in any direction. So, like I said, time was of the essence, so one of the really key parts of the project was the decision on how to actually get that Sky Park working at the top. Do you just create one big continuous piece of steelwork that forces everything to move together? Or what we actually ended up doing was articulating it through 5 different plates. So one plate attached to each of the towers, 1, 3 and 5, and then 2 bridges in between. Which is all good until you realise that there's a pool up on top. So this is actually one of those rare occasions where the engineers made a decision that they thought was necessary for the engineering, which made the architect's life very, very difficult. Normally, people would say it's the other way around. I can see Neil Stonnell there smiling at the So one of the reasons for going the articulated option was that the very basic numbers I did show that there's a huge amount of steelwork needed to force those towers to move together, but also there's a large amount of uncertainty, particularly around the wind loads and how it would interact between the 3 towers, all moving differently. So by separating them all, it took out a lot of that uncertainty. and made it a lot easier and quicker to design, which again was down to this speed thing. So it was a bit of a captain's call, not by me and my dad, but by DC Chong in Hong Kong, and the bridge team there who did a lot of the design to actually go with the articulated option. So each tower has a bridge in between it, a whole series of bearings that tie it together in one direction but allow it to move in other directions, so that when one tower moves relative to another, the bridge just rotates. Again, which is great until you get to the point where there's a swimming pool on top of it, and you realise that you need to actually bridge the swimming pool over a gap that's opening and closing up to a metre. So half a metre in each direction potentially. And so there's huge movement joints in there. And what the swimming pool architects / engineers came up with was that detail there, which is a big sort of precast C-section which sat on top of the joint on these big industrial grade rubber windscreen wipers, if you like, so that when the buildings move backwards and forwards, the C-section just slides backwards and forwards with it. So that joint just constantly leaks because you can't get proper seals in there, and all they did with that was just to put in a gutter and just keep pumping it back up into the pool. So building a constantly leaking swimming pool that just feeds itself. And that's a shot just prior to completion showing those big C-sections sitting there without anybody in it, and in the final location. So you can't swim 150 metres because you bang your head along the way in the shallow bits. And I think they've actually got banana lounges and things up on those bits at the moment there. But it's an amazing place to go and swim. I think you need to stay there if you can afford to stay there. And I used to be able to afford to stay there when they first opened it. I can't anymore because the prices are pretty high. But I'd really recommend it. It's a fantastic experience. It was funny, you know, Moses Safdie and the architects all designed this on the premise that it would be an ultra exclusive, high-end experience, and everyone kept quoting, it was Angelina Jolie and Brad Pitt at the time, they're going to be nestled in the corner, you know, sitting in Singapore swing, having a moment, and you actually go up there, and everybody did exactly what my wife and I did, which was to bring all the kids along. Actually, we invited my wife's sister and her kids, and this is like a public swimming pool with people all over it. It's just the most popular, busy place you'd ever be, which is exactly what Sheldon Adelson wanted. He wanted as many people to see this thing as possible. So if you go up just the observation deck, you can walk past the pool. So he wants it out there on show as an attractor for the casino. They're my kids. I always put that in there just to remind students, but also myself and anybody else I'm talking to, that this is why I love working on buildings where there's people involved. It's because, you know, we're creating things that are really worthwhile and fun to be around. So I think this was in Singapore, they had National Day, and they have about 4 or 5 practices, the National Day, the full-scale practices where they fly jets and helicopters with the Singapore flag. I think this was my son pointing all of the jets starting to fly over. So, thinking about how that project worked, it's what I call empathetic engineering. Eric, you know, the engineers, and Safdie, the architects, did talk before the competition was submitted, but it was more to see what was possible rather than what it should be, you know, what we might grow from the engineering. It worked though, I think, because it was a time-constrained project. It was like grabbing onto a freight train for 4 or 5 years and not being able to let go. It was just full on. And yeah, everyone was mutually dependent on each other. And it operated in a pyramid of fear that started from Sheldon Adelson at the top of Las Vegas Sands. So everybody from Sheldon had this motivation to actually make this thing work. There's a project manager, a really nice American guy, quite early on in the project, who at one of the meetings said, "We are kidding ourselves if we think we can actually build this in this time. Yeah, we need way more time than this." And by, I think that was on a Friday, by Tuesday, the next week he was gone. So there was no talk about not being able to do things. It was, what do we need to do? Money's no object. We just need to get this thing built on time and to spec. Co-located teams was really important, and the digital environment which was shared was really important as well. So all of the major steelwork packages were tendered without an architectural drawing. So all of the quantities were in the model. The 3 weeks you normally spend on a buildings project in steelwork, sorting out geometry and questions on what it should be, all of that disappeared, and the steel fabrication happened very, very quickly. And all of those decisions were conscious decisions about trying to reduce time at every step of the way. And I don't think Sean Adelson is particularly open-minded, but the client team that they had on board were a whole lot of construction managers that they use in Macau and other places, and they were fantastic. They really knew how to build stuff, and they didn't get fazed by any problem that popped up. Everyone just mucked in and actually made it work together. So it's a great experience to be involved in. So at the end, I'd say it was a very, very close interaction between the architects and engineers, and a real success story, but a little bit short of what I'd call architectural engineering. So the next project's the project to the left, which is the Singapore Flyer. It's a 150-metre diameter observation wheel in Singapore, built around about the time of SARS, if you remember SARS. But the story of the wheel probably starts with the Millennium Wheel, which I was incredibly lucky to work on as a young engineer in London under Jane Wernick, with David Marks and Julia Barfield, who are the architects. So David Marks and Julia Barfield came to Arab and said, there's a competition being run by the papers. We need a big project to mark the millennium for London, put us on the world stage. And this was their entry. In fact, they came to us with a single arm, saying we wanted a 150-metre diameter wheel. We said that the steelwork involved in that's essentially a 225-metre cantilever would be almost impossible to do. So I think at the concept stage, we convinced them to add in an extra arm, and that was their competition entry. As it happened, there's all sorts of entries, gondola rides, stand the Thames, and all that sort of thing, and the papers called off the competition and said we didn't receive any entries that we thought were worthy of giving the prize to. And so they cancelled it all, donated the prize money to charity, sold a lot of papers, and really offended the design industry in London in a big way. David Marks was an incredible guy. He's passed away, unfortunately, in the last couple of years. But he was dead set on building this wheel. He knew a lot of people and was a man of means himself. So he funded some initial studies for Arab to look at all of these different types of wheel. We continued to design this wheel. That was one of the diagrams that we sketched, that we took to David Marks and Julia Barker, just to try and plot where the project was going to go. Because we started with 1 spoke, we had 2 spokes, and why not 3, 4, 10, 200 spokes? And so this diagram, there's a couple of lines on here, and you can tell it's written by an engineer because it's got the word efficiency in there, and it's got a formula on it as well. And so the formula for efficiency was all of the things that we're putting in. So seed money, design time, resources, that was all on one side of the equation. And then the things we're getting out on the other side were the fees for people to ride, the aesthetics involved in the wheel, the effect it had on the environment, negative and positive, all of that sort of thing. And so it was a very subjective measure, but in that measure was the form of the wheel, both from an engineering point of view, which is really that black line, because over here the single arm was fantastic, but it was just extremely heavy and extremely expensive. But it scored really well on the aesthetic side. Everyone would have loved to have seen a wheel like that. So these lines were drawn as an inverse here, just so that they weren't conflicting with each other. But aesthetically, it scored really well. Whereas the other end of the spectrum is the wheel you see in your average fairground attraction, which is laced strut wheel. And it's still the most efficient way to build a wheel, actually. But nobody gets excited by one of those wheels, right? If you built that over opposite the Houses of Parliament, people would tar and feather you, I think, in London. So we went through these different options, subjectively assessing the architecture and the cost and weight to come up with what was probably the most efficient wheel. And we figured out sort of halfway through the process, actually we can put in many spokes, and if we make them big stainless steel cables, they almost come invisible like this. So it's almost like there are no spokes in it. And even when you do see them, you see them up close, and there's really elegant fittings and really well done. So, that was a solution that, wasn't the best one aesthetically, but it was pretty good. And the same with the engineering and cost. Not the lightest wheel, but pretty close to it. And so once you looked at the efficiency through that, you realise that wheel ticked all of those boxes. And if you look around the world at all of the wheels done since then, the Las Vegas High Roller, the one in Dubai, in fact the Singapore Flyer, which I'll talk about, it's that same tension wheel solution that's being used, apart from the Melbourne Star, which is a whole other lecture, sorry. And I'm not down on the Melbourne Star, by the way. I think it's a nice wheel. So that's what we ended up with as a project. This 3-chord triangular truss, these lovely, almost invisible tension spokes, and these really high-tech double curved, triple glazed units to see London from. David Marks said at the outset of this project, we need to get the architecture right because, no one will let us build something like this across from the Houses of Parliament unless it's really beautiful. And in the end, they gave them a 5-year planning permit. And David said, if we do it properly, people are going to fall in love with this wheel. It's going to be really successful, and it's just going to be there forever. And that's exactly what happened. So, and it's the same thing with the Eiffel Tower. Everybody loved it. I think it's still one of the most successful tourist attractions ever, although I'm not sure whether that's because British Airways, who ended up sponsoring it, got to write off a huge construction cost for it. But it's been granted planning permission. Just as a quick aside, and there's lots of stories on this wheel. When we first finished the design, it was 150 metres diameter, and the budget was £18 million. And Mitsubishi Heavy Industries came in at £21 million, and they were closest bidder. And they decided, no, we're going to award it to Mitsubishi, but we're going to actually award it on the basis that they value engineer out £2 million. And so they started to dumb down a lot of the connections and the detailing. A big thing they did was to change the motor-driven spherical capsules to swinging gondola capsules. And it got to the point where David Marks said, this is not the wheel that I wanted to build. If we build this wheel, it's going to be a pile of scrap in 2 years' time. And he said, I'm not going to build it if that's what it looks like. And so he, having this cherry job in his practice, wasn't a big practice at the time, just basically laid down things and said, we're not going to be building that wheel. And he let it go for another 8 or 9 months, I think. And then in the end, British Airways said, look, we really need something to mark the millennium. It's not good, just get it done. They went away from Mitsubishi, they went to Hollandia and just said, we need to get this done. They mobilised every academic in the country because time had been running out, and they did it. And the end cost, I think, was about £70 million. So they could have had the whole thing for £21 million if they just followed what their original process was, but they ended up paying $70 million to get it up there. Anyway, that's not the story. The story is the Singapore Flyer. So Singapore Flyer was a company in Singapore called Melchers, who actually sold luxury watches for a living. I don't know what a luxury watch is, but they decided that it was SARS time. They had good relations with the Singapore Tourism Board, and they decided, let's build a London Eye in Singapore, but it was a pure development project. So the first work happened in 2003, completed 2008, developer-led proposition, 90 million Singapore dollars, so an absolute fraction of the cost of the London Eye. Design motivations, it was all about the money. I mean, these guys were businessmen. They didn't really care about the architecture, apart from the fact that the Singapore government cared about the architecture. So the Singapore government weren't going to build something that put Singapore in a bad light, and so they needed to make sure they did a good job. So they got Kisha Kurokawa on as the architect, and Alec on as the engineers. In the end, Kisha Kurokawa was really just a name. There wasn't much input into the architecture at all. It was all engineering, and it was all about the dollars. And same post-war. So once they actually were given the go-ahead to build the project, it was all about getting it built quickly and cheaply. And then the way they did that was David Marks was pretty adamant about a few things. I'd call him, he was very empathetic to the engineering, but there were certain things that he wouldn't budge on. One of them was this triangular shaped truss, and the fact that the cables had to come up and reach the inside of the truss. So he could see this triangular form of rim in 3 dimensions, and these lovely cables all coming up to the middle point here, and he absolutely wanted that, and so that was a given. Another thing was that it was cantilevering over the Thames, so the width of the hub at the bottom there was constrained. I think it was about 8 metres or something, maybe, it must be more than that, maybe 12 metres. But it meant that the inclination of those cables was actually quite shallow. And so the wind blades on the capsules in the rim, the blue line arrow at the top there, they get resolved through those cable forces. And so a shallow cable force means a big force in the cable. The Singapore Flyer, what we did was actually cross them over. And we actually started off with a trapezoid rim, so 4 chords. But we found that when we actually swapped them over and we widened out the rim, we could actually get the angles on those cables to be so much more efficient that you could actually swap it, reduce the 4 chords down to 2 chords in the rim around the outside. And they're also doing the same, I should say, previously. The blue cables here, you can imagine a rim in compression, and there's nothing to stop it buckling torsionally. And so we had to actually, on the London Eye, we had to add in those 4 sets of cables there at quarter points you see to actually restrain the rim from the torsional buckling line. In Singapore, those cables did the same thing together, so it's an incredibly efficient design from an engineering point of view. And what you find is you're in this vicious circle or virtuous circle. So I'm not going to go into the detail, but the pre-stress in the cables is governed by the weight of the wheel. The more weight in the rim, the heavier the wheel, the heavier the pre-stress. And it's a vicious cycle because, well, I'll go the virtuous cycle. If you can actually lower your spoke pre-stress, then it's less compression in the rim. And so less compression in the rim, you can actually reduce the amount of steel in the rim. So less steel in the rim, it's a lighter rim. So you go around this virtuous circle where you get exponential gains in efficiency just from keeping the weight down. And the converse is true as well. So everything that was put on that rim down to the last little escape ladder was examined for weight. And the result was a wheel that was 15% bigger than the London Eye, that actually weighed 15% less. And so that's how you get down to that $90 million construction cost. You can see the cable, the capsules, no triple glazed, double curved glass. These are Coke cans on their way around. But again, appropriate for Singapore because you've got a huge heat gain, so there's a lot of air conditioning things in the tops of these capsules and shading, whereas London would have been like a microwave if you tried to build that in Singapore. So that was the end result, and I'd like to think that the engineering was had a big say in what that wheel looked like, and it actually added to the architectural solution rather than took away from it. It's different to the London Eye, and you can like it or hate it, but I think it still looks all right. The other thing I was put up is that's Charles Ferris's original wheel for the 1890 World's Fair, I think, in Chicago. So actually, when we looked at IP on these wheels, there's no difference structurally between that wheel and this wheel. It's still a compression ring around the outside with tension spokes. The only technical difference between this wheel and this wheel is the capsules. Now, these are motor-driven capsules in slewing bearings, and whoops. And Charles Ferris's wheel, just a big dining room size hanging gondolas swinging backwards and forwards. So, and you know, Ferris was doing that without computers or anything like that. So it's a real reminder that we've come a long way with technology, but it's been around for a long time as well. So looking back on it, I call this engineering led in terms of the Singapore Flyer, with a footnote to say that it was built off the architecture that was developed in London. So it would be incorrect to say that this was an engineering led project. This was really a composite of architecture and engineering put together, but very strongly dollar driven, and a very strong contracted delivery. Mitsubishi Heavy Industries ended up building the Singapore wheel. We went to their factory. They still had models of stuff that they'd built for the London Eye, so they had a point to prove that they really wanted to build this wheel to save space. And they were a very, very capable heavy steelwork contractor, and a very open-minded client who was actually willing to listen to the people we had around the table. So the last project I'll talk about is Singapore Sports Hub. I had less to do with this. I worked on the very early stages, but it was a very long gestation. So a lot of it was done after I left Singapore. First mooted about August 2001, completed 2011, sort of 10 years later. $1.3 billion, and importantly, it was a PPP. So design motivations pre-award was all about dollars. Again, it was a competition. The 3 or 4 different consortiums all vying to actually build the project. That was redevelopment of the existing national stadium, a 55,000 seat stadium, along with an indoor stadium next door. Again, had to be iconic. It's Singapore. They wanted to be a world stage. They wanted to attract people to the city, and the business model, a PPP, was going to be owned and operated for a period of time. Post-award, the architectural drivers probably took a bit of a back seat. Not to say that they weren't important, but really it was about making sure they delivered on cost and making sure that the business model was looked after. And it's a very, I haven't worked on many PPP projects, but it was great to actually be in meetings where people would be talking about maintenance and the next 10 years and when things would have to be it's a totally different way of thinking. In buildings anyway, I know there's a lot of infrastructure people around this road, but it's something that we buildings people I think really need to learn. Fantastic result. That's the roof. It's ETFE cushions lit up. The seating moves in and out so they can cater for almost any sport they need to. You can play cricket there. That's the whole project. There's swimming pools and multi-purpose arenas and retail centres through here. This MRT station wasn't a part of the project, it had already been built, and the indoor stadium on the bottom right there. But really the main part of the project was that dome, and the dome was conceived by Jay Parrish from Arup Associates, or Arup Sport I should say, in the UK. And Jay is a very technically minded architect, and he wanted to build something huge and iconic, but really efficient at the same time to keep the cost equation down. So it's still, I think, the biggest dome in the world, 312 metres. That gives you a bit of an idea of the scale. They're 5 metres deep at the peak of the roof, and there's large lines which make sure you get the two-way shell action that makes domes really efficient. And So when you're talking efficiency, when you're designing building roof structures, there's a rule of thumb that says anything up to about 40 metres, you can see down here, you generally can't get away with anything less than 40 kilograms of steel per square metre because you've got purlins and secondary steelwork and all this sort of thing. Once you get above 40 metres, you get a bit more leeway to do stuff. But in general, there's a linear line to say that the more span you add to the roof, the more kilograms per square metre you add to the roof. And the rule of thumb is if you build a 100 metre span roof, you're up to about 100 kilograms per square metre, and so on up that line. But you can see where that dome is, the Singapore dome, which is just over 300 metre span, is sitting down around about 120, 130 kilograms per square metre. The reason there's 3 dots there, that was this graph was one that I'm looking at. 3 different steel grades, so high strength, medium strength, low strength, and just figuring out what they should be using in terms of materiality. But it's probably a third to a half of the cost of a normal roof that you would expect to stand that way. So again, really, that was front and centre in Jay Parrish's mind, and Dragage and Bouygues, who were the contractor leading the PPP when they put it together. There was a worry that it wouldn't be iconic enough. It's just a simple dome. Is this iconic architecture? There's a lot of debate about that. Jay Parrish was adamant, you build something this big, and once we look at all of the detail, we will turn it into something special. And that's what they did. They looked at all of the engineering around thermal comfort. Not many stadiums of this size are actually air conditioned. This is an air conditioned stadium. They did it through trickle feeding cool air underneath every individual seat so that it formed a boundary layer that trickles down the stands. So you're actually sitting in air conditioned air while you're in the stadium. And I think it's about 15% of the costs of equivalent stadiums around the rest of the world in terms of providing air conditioning. A lot of the thermal comfort calculations that were done were all about promoting airflow, and so huge louvers around the sides of the dome to try and encourage everything you could do to get cross ventilation. So the moment in Singapore, because it's so humid, the moment you get any movement of air over your skin, you get the back really cool and you immediately feel more comfortable. Really high specs on the solar radiation shielding. There's an operable roof. Put into it. But you can see the detail that came out of it. Again, huge louvers providing cross ventilation. These ETFE cushions, which are the perfect thing to put on a moving roof because they're light, there's no secondary steelwork. You can move them backwards and forwards, and you can see how they could even light them up into the image of a Singapore flag when they needed to National Day. So lots of really clever thinking on the way through, but really the big architectural engineering decision in my book is that decision to go for this huge dome in the first place and really give that consortium a big cost advantage over their competitors. So I would call this proper architectural engineering in terms of an outcome. Co-located multidisciplinary team is a really big factor. Did the architecture and the engineering, and they did it on site in Singapore with the contracting team. PPP, those whole of life drivers, just meant all of the conversations were about performance for the whole life of the project rather than just what they're going to build for the photos at opening. Really heavy use of digital modelling, so lots of clash detection and everything else. The whole job was built in BIM before it was built properly. Bouygues were a fantastic multi-faceted delivery team. Again, in all of these projects, the contractors brought as much to the table as the engineers and architects did, and an open-minded, educated client in terms of the Singapore government, who also had a very, very strong part in the way that they ran that PPP. So I think it gives you a bit of a taste of how architects and engineers can work together on these projects and what some of the outcomes can be. And it's not to say that Marina Bay Sands isn't a great project because it is empathetic engineering. It's a fantastic project. There's some brilliant stuff done on that job, but it's really when you get to these decisions about the wheel with tension spokes and these pure dome decisions, that's what I call architectural engineering, where there's an engineering driver and then it gets worked together with the architect to actually create something that's, I would say, adds to the architecture rather than takes away from it. So the holy grail for architectural engineering is that the sum should be greater than the whole should be greater than the sum of the parts. So just to talk a little bit about where I've come from then, because I'm a structural engineer by training, so a lot of my thinking is structural engineering. Since I've been at Melbourne Uni, I've realised I think the big gains for architectural engineering are in sustainability engineering, or sustainability design, I should say, so energy in buildings and those sorts of things. And we've done quite a bit of work at Melbourne Uni looking at how architects and engineers interact. So we've run what we call the integrated design studios. We essentially had architects and engineering students in the same studio together, master's level students designing fictitious projects with real clients, academics obviously, and also consultants. So the consultants would come in and actually help advise the architects and engineers. And so we actually studied how the students interacted and really tried to attack a few different building typologies using integrated design principles. And this is one of the outcomes, this graph. So we looked at net zero potential as the basis of the studios. So if you read this graph, 100% business as usual. So the consultants would actually do some research on the different building typologies and say, facility in this typology generally uses this much energy. And then they would go through the design with the students, architects and engineers, come up with a design and actually see how much they could use. So the dark green lines here are the reductions in energy consumption. We then put PVs on top generally, so we generated some energy on site. And you can see for schools and emergency facilities or ambulance stations, we could absolutely get to zero carbon. For some of these other building typologies, swimming pools, aged care, laboratories, community centres, we didn't do quite as well, but we took a huge chunk out of it. But essentially through, and this is not using space age technology, this is all tried, tested, trusted technology that we have now. The students were ending up with anywhere between 15 and 60% reductions in business as usual. And that's why it's important. 20% of all electricity consumed is through HVAC in the building industry. So if you can take 15 to 60% of that away, that's a lot of energy and a lot of carbon saved through the process. Just a bit of a plug for the work that was done. That's the report. Chapter 3, we'll probably do a bit more work to get this out there. Chapter 3, we learned a lot about how to get integrated design happening on projects. So I actually wrote a bit on that, recommendations for industry. And then chapter 4 is a net zero carbon catalogue, which talks about the design moves you can make or that the students make to actually achieve some of those savings. And that's where we are. So Melbourne University, along with Swinburne and Monash, and hopefully others soon, are now running architectural engineering degrees. So at Melbourne, you do a Bachelor of Design or Science, really, you can do design or science, and from there go into an engineering master's for an extra 2 years, or an architectural master's for 2 years, or you can spend 3 to 3.5 years, so get more bang for your. And you basically cover the core of both of those degrees for architectural engineering, so it's essentially a double degree course. And I spoke to Chris, who visited from the States today. There's a big groundswell. I mean, Melbourne is behind the game when it comes to architectural engineering and what can be done. So there's a lot of scope out there to do things better.